Welcome to the course on advanced power electronics. So we'll have a topic on today: class E resonant converter and zero voltage switching converters. So in this category, we have a class E resonant inverter. So this class E resonant inverter, a class E resonant inverter uses only one transistor and has low switching losses and hence very high efficiency is achieved. The load is supplied through sharply tuned series resonant circuit resulting in an almost perfectly sinusoidal current, and this inverter is normally used for fixed output voltage. However, the output voltage can be varied by varying the switching frequency, and the switching device have to withstand high blocking voltage. Hence, it is normally used for low power application requiring less than 100 watt, particularly in high frequency electronics lamp ballast. This is a typical circuit of class E resonant converter where we have typically a DC source with a LE inductor, then typically a switching device with anti-parallel diode, and if it is not inbuilt, then we connect separately, and then a capacitor followed by L and C component and the load. So above figure shows the circuit diagram of class E resonant inverter, and if the switch does not have a built-in anti-parallel diode like MOSFET, and external anti-parallel diodes as shown by dotted line is in the figure above needs to be connected. So there are modes of operation. So the mode first, here it is like when this switch is closed as it is shown, and current flow through this switching transistor IT, and how the current flows in the input output. So mode 1, during this mode the transistor Q1 is turned on and the equivalent circuit is shown in this figure, and the switching current consists of source current, typically IS, and the load current IO. To obtain almost sinusoidal output current, the value of L and C are chosen to have high quality factor and low damping ratio, and where this Q should be greater than 7 and delta should be less than 0.072 in general for the design purpose. The above range has been obtained after keeping in mind the efficient zero voltage switching condition after observing the class E resonant inverter waveform for different loading conditions, and the switch is turned off at zero voltage. When the switch is turned off, its current is immediately diverted through capacitor CE. And this is the mode 2 circuit. During mode 2, transistor is turned off and the equivalent circuit is shown in the above figure, and the capacitor IC becomes the sum of the source current and the load current, as you can see from this equivalent circuit. The switch voltage rises from 0 to maximum value and falls back to 0 again, and when the switch voltage falls to 0, that is IC equal to C dV by dt is negative. Hence the switch voltage will always tend to be negative, and to limit this negative voltage, an anti-parallel diode as shown in the circuit diagram by the dotted lines is connected, and if the switch is a MOSFET or a reverse conducting IGBT, the negative voltage is then limited by the built-in diode or connected external diode to a value equal to the diode forward voltage drop. And these are typically voltage waveform. You can see it like a input and output voltage here, and then typically the DC current, and then the transistor current, then the capacitor current, and then of course the transistor drop, and you see the positive voltage always there. So coming to mode 3, this mode occurs if the switch voltage falls to 0 with a finite negative slope. The equivalent circuit is similar to that of mode 1 except the initial condition. The load current falls to 0 at the end of mode 3. However, if the circuit parameters are such that the switch voltage falls to 0 with a 0 slope, there is no need for diode, and this mode will exist. Like here is inverter, so we have a alternate current in the output. Like so, to find out the parameters, optimum parameters for the condition Vt equal to 0 and dV by dt equal to 0. So the first condition called zero voltage switching, and the second condition called zero derivative switching or zero slope switching. And this smaller are the parasitic component. The closure is the operating point to the optimum condition, and the general values of optimum parameters are found. L equal to 0.4001 R divided by omega s, and C equal to 2.165 divided by R WS, and omega s L minus 1 upon omega s C equal to 0.0 3533 R, where omega is the switching frequency in radian per second. Now coming to that was class E inverter. Now there is another case, can be a class E rectifier. Class E resonant rectifier can be used this converter as a rectifier. So this class C resonant converter, a resonant DC-DC converter consists of high frequency resonant DC to AC inverter and high frequency rectifier. And this configuration suffers from disadvantages such as conduction and switching loss, parasitic oscillations, and high harmonic content of the input current. A class C resonant rectifier overcomes these limitations and uses the principle of zero voltage switching of the diode, and that is why the diode turns off at zero voltage. And if the diode is replaced by controllable switch, typical, for example, a power MOSFET, a class C synchronous regulator rectifier is obtained. So the AC source and the rectifier can be coupled by an isolation transformer to provide the desired AC to DC voltage conversion factor and also to comply with the safety regulation. And this is a typical circuit of class C resonant rectifier. So you can see how the typically elements are there, a small capacitor across the source, then the inductor, and across the diode we have a capacitor junction capacitor A and C, and then the output capacitor, filter capacitor, and R in then the load in parallel to filter capacitor. So above figure shows the circuit diagram of class C resonant rectifier, and the diode junction capacitance Cj is included in the resonant capacitance C and therefore does not adversely affect the circuit operation, and the filter capacitance Cf is assumed sufficiently large so that DC output voltage V0 is constant. And now in this case also class C resonant rectifier, coming to the mode 1, you can see the equivalent circuit here out is really a mode 1 between the source, current flows through the inductor IL, and then see the voltage across VC and the typically the output voltage VO. So here also the mode in mode 1, during this mode the diode is off, and let the input voltage Vs equal to Vm sin omega t. Here it's a kind of rectifier. So the value of L and C are such that omega L equal to 1 upon omega C at the operating frequency F. The voltage appearing across L and C is VLC equal to Vs sin omega t minus VO. And in case of the mode 2, you can see the equivalent circuit how it looks like. So in mode 2, during this mode the diode is on, and the voltage appearing across inductor is the VL equal to Vs sin omega t minus V0, and when the diode current ID, which is the same as the inductor current, reaches 0, the diode turns off, and at turns off ID equal to IL equal to 0 and VD equal to VC equal to 0. And these are the typical waveform. You can just see how the typically supply voltage, then how the currents, inductor current as well as output current, and then the diode currents and output current, and then the typically your capacitor current. So diode voltage is 0 at the turn off, so thereby reducing the switching losses, and the inductor current is approximated by IL equal to Im sin omega t minus phi minus I0, where Im equal to Vm upon R and I0 equal to V0 upon R. So when the diode is on, the phase shift is 90 degree, and when the diode is off, it is 0 degree, provided that omega L equal to 1 upon omega C, and the peak to peak current is 2 Vm upon R. Now coming to the soft switching, this is normally the soft switching obtained by two methods, zero voltage switching and zero current switching. So first coming to this soft switching in these converters, the main causes of soft switching losses in converter include the diode recovery, reverse recovery, semiconductor output capacitance, and the tail current in case of IGBT. And the soft switching involved mitigation of one or more the device loss mechanism in a PWM converter, and the operation of semiconductor device during a given turn on and turn off switching transition can be classified as hard switch, zero current switch, or zero voltage switch. And the resonant switch converters are broad class of converter in which the PWM switch network of a conventional buck boost or other converters is replaced with a switch cell containing the resonant element. These resonant elements are positioned such that the semiconductor device operates with zero current or zero voltage switching, and such that one or more of the switching loss mechanism is reduced or eliminated. And soft switching converter can exhibit reduced switching loss at the expense of increased conduction losses. The phenomena of switching loss is different for different power semiconductor devices, and during the diode turn off, That is, reverse recovery causes losses in other converter element, and the MOSFETs lose energy stored in their output capacitance during the turn on, while the IGBTs suffer energy loss from the current tailing during the turn off. And this is the typical case when we have a hard switching of the diode. So you have a diode here, voltage is across VT and current through it IT, and how the current IT here look like, and you have a certainly during turn off you just see the big tail with the resonance. I mean that causes the typically the to increase losses during turn off, and how the voltage across the diode, reverse voltage across the diode when it's not conducting. I mean, and when it is conducting, it's a 0 volt. So the above circuit showed the conventional hard switch pendulum buck converter. As you can see, the switch like a simple buck converter with the diode voltage and current waveform VT and IT clearly shows about the hard switching. So the diode turns off when the transistor is turned on, and the reverse recovery process leads to a negative peak current of large amplitude. The diode must immediately support the full reverse voltage VG, and hence both VT and IT must change with large slopes during reverse recovery. And energy loss during switching is WD equal to VG QR plus TR VG into I. And typically coming to the circuit here again with a zero current switching. If we have a zero current switching with, we have a typically resonant element CR and LR. I mean the CR in parallel with the switching device, LR is in parallel in series with the diode. So how the current really reverse recovery current reduces to quite low value, and how the voltage across the diode is also across here it is. So now resonant tank with LNC is connected, and the resulting diode waveform IT changes with the limited slope as shown in the figure. So well, the diode reverse recovery process commences when IT passes through 0 and becomes negative, and energy WD is stored in the inductor at the end of reverse recovery time, and then circulated between LR and diode's capacitance CJ, and that WD equal to VG into QR. So zero current switching leads to lower loss because the reduced di by dt leads to less recovery, recovered charge QR. And coming to typically here how this equal, you can see the current really the area and the voltage across the typically the diode. So in above circuit, the output inductor LR acts as a tank inductor and causing the large current ripple and polarity reverse in IR. So now while conducting, the diode current equals to IR. When IR turns negative, the diode conduct until its charge QR is depleted, and after which IR flows through CR and the diode capacitance CJ. The diode voltage and current both change with a limited slope in this type of switching, and the loss induced by the diode recovery process is negligible. So zero voltage switching at the turn off transistor of a diode is the preferred approach that leads to minimum switching loss, and zero current switching at the turn off transistor can be problematic because of the high peak inverse voltage induced across the diode by ringing. Now coming to typically here the hard switching in MOSFET, you can see the waveform, I mean the current through the MOSFET and the voltage across the MOSFET as shown in the figure, and how current looks like. So you can see current through the MOSFET is high when the voltage across is reasonably, so certainly losses are substantially high. So the most significant component of switching loss in MOSFET of this circuit are the loss induced by the diode reverse recovery process as it shows the peaky current, and the loss of energy stored in the MOSFET output capacitance CDR. Both loss mechanisms occur during the MOSFET turn on process. So with the fast gate driver, MOSFET turn off switching losses are minimal due to substantial output capacitance which holds the voltage VT near zero during the transition. However, during the MOSFET turn on, a high peak current from diode reverse recovery and output capacitance causes significant energy loss in the hard switch transition. Moreover, when a MOSFET operates with the hard switching and when substantial inductance is present in series with the MOSFET, then significant ringing is observed in the MOSFET voltage waveform. And typically, of course, coming to this mode of operation, the circuit shows you can see clearly how the current in the device and how the voltage across the device builds up. So certainly current goes to zero when voltage is zero, and current builds up again when voltage is 0. So that's why called zero voltage switching. So the above circuit shows that zero voltage switching operation for a MOSFET in a buck converter, and zero voltage switching can prevent both diode reverse recovery as well as semiconductor output capacitances from inducing switching loss in MOSFET. So the converter circuit naturally discharges the energy stored in CDS before the MOSFET is switched on, and when the drain to source voltage VT passes through zero, the MOSFET body diode becomes forward bias, and the MOSFET can then be turned on at a zero voltage without incurring turn on switching loss. The MOSFET turn on transistor must be completed before the tank inductor current IRT becomes positive, and zero current switching does not affect the switching loss from MOSFET output capacitance and may have little impact on the diode recovery loss. Therefore, it offers minimal improvement in the efficiency of MOSFET based converter. So now coming to zero voltage switching with the quasi-resonant converters. In quasi-resonant converter, of course, we consider the internal capacitance of the switch. As you can see here, we have a zero voltage switching resonant switch like here, across which capacitance is there and inductor there. So the switches of ZVS resonant converter turn on and turn off at zero voltage. So if the adjoining circuit, the capacitance is connected in parallel with the switch S1, as it is shown here in the figure, to achieve ZVS, and the internal switch capacitance Cj is added to the capacitor, and it affects the resonant frequency only, therefore contributing no power dissipation in the switch. And you can just see how switch, then anti-parallel diode and capacitance and as well as inductor are there in case of half wave configuration. So if the switch is implemented with the transistor Q1 and the anti-parallel diode D1, as shown in this figure, the voltage across C is clamped by D1, and the switch is operated in a half wave configuration. Then coming to full wave configuration, that we connect the diode in D1 in series of Q1 and then L and C. So in case of, if the diode D1 is connected in series with Q1 as shown in this figure, the voltage across C can oscillate freely now, and the switch is operated in full wave configuration. Now typically in this circuit with the full circuit here, you can just see where typically we have a capacitance in parallel to the switch and then inductor followed by, of course, the LC filter and with the filling diode. So circuit operation can be divided in 5 modes. So we shall define the time t equal to 0 at the beginning of each mode for simplicity of the analysis. So in case of mode 1, this mode is valid from time 0 to t1. So both switch S1 and diode DM are off. So capacitor C charges at constant rate of load current I0. As in the shown circuit, the capacitor voltage Vc which rises is given by Vc equal to I0 upon C into T, and this mode and at the time t equal to t1, when Vc at the t equal to t1 equal to Vs, and that is t1 equal to Vs C upon I0. Now coming to mode 2, as you can see in the circuit how the current IL and I0 in the output move with the filling diode. So mode 2, this mode is valid for t varying from 0 to t2, and the switch S1 is still off, but diode DM turns on, and the capacitor voltage is given by typically Vc equal to Vm sin omega 0 t plus Vs, where Vm equal to I0 under root LC, and the peak switch voltage occurs at t equal to pi by 2 under root LC, and the peak switch voltage given by Vt peak equal to Vc peak equal to I0 under root L upon C plus Vs, and the inductor current is given by IL equal to I0 cos omega 0 t, and the mode ends at t equal to t2, and Vc equal to t equal to t2 equal to Vs, and IL equal to at t equal to t2 equal to minus I0. Therefore, t2 equal to pi under root LC. Now coming to the mode 3, as you can see typically in the figure, so this mode is valid for time varying from 0 to t3, and the capacitor voltage that falls from Vs to 0 is given by Vc equal to Vs minus Vm sin omega 0 t, and the inductor current is given IL equal to minus I0 cos omega 0 t, and this mode and at t equal to t3 when Vc in bracket t equal to t3 equal to 0 and IL at t equal to t3 equal to IL3, and thus t3 equal to under root LC sin inverse x, where x is equal to Vs upon Vm or equal to Vs upon I0 under root C upon L. Now coming to mode 4, as you can see the circuit here, the IL3 is just reversing. So mode 4, the valid from 0 to T4, and switch S1 is turned on, and diode TM remains on, and the inductor current which rises linearly from IL3 to I0 is given by IL equal to IL3 plus Vs upon L into T, and this mode and at T equal to T4 when IL at T equal to T4 equal to 0, thus T4 equal to I0 minus IL3 into L upon Vs, hence the IL3 has a negative value. Now coming to mode 5, as you can see the circuit here simply. This mode is valid from 0 to T varying from 0 to T5. So switch S1 is on, but diode DM is off. The load current flows through the switch, and this mode ends at T equal to T5 when S1 is turned off, and again the cycle is repeated. Thus T5 equal to T minus in bracket T1 plus T2 plus T3 plus T4. And these are the typical waveform if you can look into for how it is in T1, then T2, then T3, T4, and T5 for all 5 modes. The voltage across the capacitor and typically the output current and the inductor current here in the waveform. The capacitor voltage, inductor current, the ZVS converter. So the waveform for IL and VC, so the peak switch voltage VT is dependent on the load current I0, and therefore a wide variation in the load current results in a wide variation of switch voltage. For this reason, the ZVS converters are used only for constant load application, and the switch must be turned on only at 0 voltage, otherwise the energy stored in C can be dissipated in the switch. And to avoid this situation, the antiparallel diode D1 must conduct before the turning on the switch. Now coming to configuration of ZVS DC-DC converters, so similar to buck converter, the other resonant DC-DC converter can be obtained by adding a resonant capacitor CR in parallel with the switch and the resonant inductor in series with the series or parallel of the switch and the resonant capacitor in conventional PWM converter. So resonant inductor LR is much lower than the filter capacitor L, and the resonant capacitance CR is much lower than the filter capacitor. So all the DC-DC converter also can be made to operate resonant converter with the slight modification in the circuit with the resonant circuit. Like as you can see, the capacitance in series with the typically in buck converter, the capacitance in parallel to the switch and series inductor, and then you can have a ZVS boost converter, again the capacitance in parallel and the inductor in series with typically with the switch. Similarly for buck boost converter, you can see the inductor in series and then the capacitance in parallel of the switch. Similarly for ZVS isolated buck boost converter or flyback converter, you can see capacitance in parallel to the switch and inductor in series with the device. So all these converter can be converted back into resonant converter, and in these converter only we like to operate on high switching frequency so that even the filter size as well as transformer size can be reduced. Like similarly ZVS your converter, where we have inductor in series with the device as well as capacitance in parallel, and then ZVS isolated current converter, inductor in series and the capacitance parallel of the switch, and remaining circuit remain the same as the typically a conventional converter. Isolated and non-isolated both category are shown here. Then the typically ZVS SEPI converter, here also capacitance we connect in parallel switch and inductor in series with the switch for causing the resonant circuit. And similarly for isolated SEPI also we connect the capacitance in parallel and inductor in series with the remaining circuit remains the IGT. So it becomes the resonant circuit, you can call it become the part of your switch. Similarly ZVS 0 zeta converter, so we have a typical capacitance in parallel and series inductor in series with the device, and similarly for isolated also capacitance in parallel and series in a series inductor in series with the switch. Like so is the typical circuit of ZVS boost converter. Here you can say it's a simple boost converter, but we are having a capacitance CR in parallel to the switch and LR inductor, resonant inductor in series with the circuit to make the resonant circuit to keep the typically your 0 voltage switching for the switch. Like so circuit diagram of ZVS converter, boost converter with current through and voltage across the various components. So the analysis of the above circuit can be done similar to the ZVS buck converter. So you can say here again typically the 4 mode, when starting first mode your 0 to T1 when your typically switch is on, so it means the circuit completed through the series inductor, and when T1 to T2 the mode 2 when switch is again on, and typically you can call it how the current but diode is off. That you can clearly see here how the circuit is there. And for third mode T2 to T3, here your typically you can say switch is also off as well as your switch is off as well as the your diode is also off. So path is through resonant capacitor like. So then fourth is switch is off and diode is on. So you can clearly see the typically, the resonant circuit of the switch comes in parallel with the source, and then the diode connect to output voltage like. And these are the typical waveform of ZVS boost converter, starting with the gate pulse of the switch, then how the resonant inductor current, and the switch current, and then typically the switch current, and followed by your capacitor current during the commutation like. So you can clearly see how the switch is switch off zero, typically during zero voltage switching. And here it is typically you can call it the voltage here, then the inductor voltage, then the diode current, and typically the diode voltage. So you can say how typically the voltage across the different and current through the different components are there in this zero voltage switching boost converter. Now coming to ZVS buck boost converter, where again we are connecting a resonant capacitor in parallel to the switch, as well as the inductor in series with the switch. As you saw there, remaining elements remain same as normally the buck boost converter. So unless of this circuit can be done similar way as a ZVS buck converter. So the first mode is your 0 to T1, where the switch is on, diode is on, as you can see here. And the second part is when switch is off and diode is off, switch is on, diode is off. And the third mode is T to 3, where switch is off and diode is also off. And fourth mode is when switch is off and diode is on. So you can see how your capacitance and the inductor comes in series with the circuit like. And the waveform, typically you can say how the gating, when you apply the gate pulse, how typically your the current of the inductor, current of the switch, as well as the current in capacitor changes, and according to the voltage across the typically the switch as well as the inductor voltage, diode current, diode voltage are shown here like. Now coming to two-quadrant ZVS resonant converter. So two quadrant means you are using a two switch here, where of course we have a diode and capacitance connected in parallel, and then we have typically the inductor and capacitance filter and the diode. The above circuit shows the circuit diagram of two-quadrant ZVS converter. So here C plus equal to C minus equal to C by 2 as it is shown in the figure, and the inductor L has a small value, it has such a value so that it forms a resonant circuit. The resonant frequency is F0 equal to 1 upon under root 2 pi under root LC, and it is much larger than the switching frequency FS. So assuming the filter capacitance C is pretty large, so load is replaced by a DC voltage source, and the circuit operates can be divided in 6 modes. So coming to mode first, as you can see equivalent circuit, the switch is on. So assuming the initial current IL equal to 0, the inductor current is given by IL equal to Vs upon L into T, and this mode ends when the voltage on capacitor C plus is 0 and the S plus is turned off, and the voltage on C minus is typically Vs. Now go to mode 2. Here in case of the mode 2, you can clearly see the switch S plus and S minus both are off, and the mode begins with the C plus having a 0 voltage and C minus having a Vs as shown in the figure here. And the equivalence of this mode can be simplified to a resonant circuit of C and L with the initial inductor current IL1. So current IL can be approximated represented by L equal to Vs minus VDC under root L upon C sin omega 0 T plus IL1, and this V0 can be voltage V0 can be approximated fall linearly from Vs to 0, and that is V0 equal to Vs minus VSC divided by IL1 into T, and this mode ends when V0 becomes 0 and diode D turns on. So here typically the mode 3, where you can say the diode D1 is turned on and current IL falls nearly from IL to typically to IL equal to 0. And in case of mode 2, you can see how really the current changing, and typically here the mode 4 S1 is turned on, S minus S1 is turned on, and when the IL and V0 becomes 0, IL continues to fall in the negative direction to IL4 until the switch voltage becomes 0 and IS minus is turned off. And coming to mode 5, as you can see in the circuit here, equivalent to which becomes equivalent to combined C. So switch S plus and S minus both are off, and this mode begins with C minus having 0 voltage and C plus having a Vs, and similar to the mode 2, and the voltage V0 can be approximated to rise linearly from 0 to Vs, And this modes and when V0 tends to become more than Vs and diode D1 turns on. And mode 6, as you can see in the circuit, where D plus is turned on and IL falls from IL5 to 0, and this modes and when IL equal to 0 and S plus is turned on and the cycle is again repeated. And these are the typical waveform for all the modes, where you can see typically T1, T2, T3, T4, T5 and T6, and then again the operation repeats in the similar manner, and how the position of conduction and of different switches as well as diodes are there. So the output voltage can be made almost square wave by choosing the resonant frequency for much larger than the switching frequency, and the output voltage can be regulated by frequency control. So switch voltage is clamped to only Vs, and however the switches have to carry IL, which have high ripples and higher peak than the load current I0, and the converter can be operated under a current regulated mode to obtain the desired waveform of IL. Now coming to numerical examples. So starting with the first numerical example, a class C resonant inverter operates at a resonance and has a Vs equal to 12 volt and R equal to 10 ohm, and the switching frequency of S equal to 25 kHz. So determine the optimum value of L, C, CE and LE, and also find the damping factor and resonant frequency, and consider Q equal to 7. So solution given Vs equal to 12 volt, R equal to 10 ohm, and omega S equal to pi Fs equal to 5 into 25 kilohertz equal to 157.1 kiloradian per second, and L equal to 0.4001 R divided by omega S. Putting the value, it comes 25.47 microhenry. And coming to CE equal to 2.165 divided by R omega S. Putting value, it comes 1.38 microfarad. And LRQ R upon omega S, and putting value, it comes 445.63 microhenry. Moreover, for optimum value, omega S into L minus 1 upon omega SC, that is equal to 0.355 R, and from which we get the putting value, we get the C equal to 0.0958 microfarad. So coming to example 2, the class C rectifier supply a load power of PL equal to 400 milliwatt and at V0 equal to 4 volt, and the peak supply voltage is VM equal to 10 volt, and the supply frequency F equal to 250 kHz, and the peak to peak ripple on the DC output is delta V0 equal to 40 millivolt. Determine the value of L, C and CF and the RMS and DC current of L and C. So, solution given VM equal to 10 volt, VO equal to 4 volt, delta V equal to 4 millivolt, and F equal to 250 kHz. And to start the design process, assume a suitable value of for C. So let the C equal to 10 nanofarad, and let the resonant frequency be same as the switching frequency, F0 equal to F equal to 250 kHz, and from this we get the typically L value of putting in formula, that is equal to 40.5 microhenry. And to find out the value of filter capacitor, first calculate the average current. So PL equal to V square by R. So here we get the R equal to 40 ohm, and then I0 equal to V0 upon R, that comes 100 milliampere, and the value of capacitance CF is given by CF equal to I0 divided by 2F delta V, and it comes 5 microfarad, and IM equal to VM upon R, that comes 250 milliampere, and RMS inductor current IL equal to IL RMS and under root 100 square, that is typically I0 square plus your typically IM square by 2, so 250 square by 2, that becomes 203.1 ampere. And the ILS DC comes 100 milliampere. The RMS current of capacitor is equal to IC RMS equal to 250 by root 2, that comes 176.78 milliampere, and IC DC is equal to 0. So coming to example 3, a class C inverter operates at resonance and has PS equal to 24 volt and R equal to 10 ohm, and the switching frequency Fs equal to 25 kHz, and the inductor L equal to 450 microhenry, and C equal to 100 nanofarad. To find the damping factor and resonant frequency, so the solution, the damping factor is delta equal to P R by 2 under root L C upon L. Putting value, it comes 0.0745, and the resonant frequency can be found out, F equal to 1 upon 2 pi under root LC, so it comes 23.73 kilohertz. Coming to example 4, a ZVS resonant buck converter supply a load power of PL equal to 1 watt and VO equal to 5 volt. The supply voltage VS equal to 15 volt, operating frequency F equal to 40 kilohertz, and the values of L and C are L equal to 150 microhenry and C equal to 0.05 microfarad. To determine the peak switch voltage, VP and IP, And solution, the average load current can be found from the output via and load voltage equal to I0 equal to PL upon V0, that is equal to 1.5 equal to 0.2 ampere. So since the inductor is connected in series with the switch, the peak of inductor current will be same as that of switch in the positive direction. And so IT peak will be equal to I0, that is equal to 0.2 ampere, and the peak voltage across the switch can be found out like V peak equal to I0 under root L upon C plus Vs, and putting value it comes 25.95 volt. Yeah, coming to example 5, the class C rectifier supply a load power of PL equal to 1.5 watts at VO equal to 5 volt, and the peak supply voltage is your VM equal to 12 volt, and the supply frequency is F equal to 350 kHz. The peak to peak ripple on the DC output voltage is delta V equal to 0 equal to 20 millivolt, and determine the A value of L, C and CF, and B the RMS and DC current of L and C. So for the solution, the load resistance R equal to V0 square upon PL. So putting a value it comes 16.67 ohm, and DC load current is now I0 equal to V0 upon R. Putting a value it comes 0.3 ampere. And resonant frequency is assume as F0 equal to 350 kHz, and then C, considering C equal to 10 nanofarad. So from F0 1 upon 2 pi under root LC. So we get L equal to, from this formula, around 20.7 microhenry. And filter capacitor is obtained C F equal to I0 upon 2F into delta V. So it comes around 21.43 microfarad. And the peak inductor current IM equal to VM upon R, that comes 0.72 ampere. So RMS inductor current is IL RMS under root I0 square plus IM square by 2 under square root of that. So it comes typically IL RMS becomes 0.61 ampere. And the DC inductor current is IL DC equal to I0 equal to 0.3, and RMS current of the capacitor C equal to IC RMS equal to IM divided by root 2, it comes 0.51 ampere. And the DC current of the capacitor C equal to IC DC equal to 0. So coming to example 6, a ZVS resonant buck converter supply a load power of PL equal to 2 watt at VO equal to 10 volt, and the supply voltage VS equal to 20 volt. The value of L and C are L equal to 200 microhenry and C equal to 0.1 microfarad. To determine the peak switch current I peak and the operating frequency F for resonance. So average load current is given by I0 equal to PL upon V0, that comes 0.2 ampere, and this value serves as a basic baseline for determining the peak current in the switch. So the peak switch current same as the inductor current, that is I peak equal to I0 equal to 0.2, and the resonant frequency is given F equal to 1 upon 2 pi under root LC. Putting value comes 30.5 kilohertz. So coming to example 7, a ZVS resonant buck converter operates at F equal to 50 kilohertz. The load power is PL equal to 1.5 watt, and the supply voltage is VS equal to 12 volt. So peak switch voltage is PP equal to 20 volt. Find the value of L and C. The solution, the average load current can be found out I0 equal to PL upon Vs, that is equal to 0.125 ampere. So using the expression of peak voltage for the resonant buck converter, Vs peak equal to I0 under root L C upon L plus Vs. So it comes from this, we get under root LC, and from which we get typically F equal to, putting value we get the 450 kilohertz, we get the L value equal to 4960. So C comes from here typically around 0.02 microfarad, and L comes around 8.2 millihenry. So small value of questions and large inductor confirm that the converter operation and ensuring proper resonant behavior while maintaining the low current. So coming to example 8, a class C rectifier is used to supply a load with a power PL equal to 500 milliwatt and a output voltage of VO equal to 5 volt. The peak supply voltage is VM equal to 12 volt, and the supply frequency is F equal to 300 kilohertz. The permissible peak to peak ripple and the DC voltage is delta V0 equal to 50 millivolt. So determine the value of L, C and CF and the RMS and DC current for the inductor L and C. So solution for given VM equal to 12 volt, V0 equal to 5 volt, delta VM 50 millivolt, F equal to 300 kilohertz and PL equal to 500 milliwatt. So assuming the value C begin to design process, let the C 12 nanofarad and let the resonant frequency to be the same as switching frequency F0 equal to F equal to 300 kilohertz. So from this relation we get the L equal to 23.5 microhenry. and we can get the load equivalent resistance P0 upon PL, putting value it comes 50 ohm, and for filter capacitor CF, putting value I0 upon 2 F delta V, so it comes getting I0 V0 upon R 100 milli, and CF comes 3.33 microfarad. And the RMS current of the inductor IL RMS is equal to under root I0 square plus IM by root 2 square. So putting IM equal to VM upon R, so IM comes 12 upon 50, that's 240 milliampere. And then putting a value of IL RMS comes at 210.9 milliampere, and RMS current of capacitor is IC RMS equal to IM by root 2, that is 240 by root 2, that is equal to 69.7 milliampere. So coming to example 9, a ZVS resonant buck converter has L equal to 100 microhenry and C equal to 0.2 microfarad. The operating frequency is F equal to 25 kilohertz and supply voltage is Vs equal to 24 volt. The load resistance R equal to 500 ohm. Determine the load power PL if the load voltage is V0 equal to 12 volt and the peak switch voltage V peak is P. The solution, the load resistance given by R equal to V square by PL, and the reasoning to find value PL equal to V square by R. So typically substituting V0 equal to 12, so load resistance comes 500 ohm and PL comes 1200 by 500, so it comes 0.288 watt, and the peak voltage is determined Vp equal to L0 under root L upon C into plus Vs. So first to calculate I0 is V0 upon R, so putting value it comes 0.024, and then Vp comes putting value of this, it comes to 24.54 volt. So the peak switch voltage is only slightly higher than the supply voltage Vs and demonstrating efficient energy transfer through resonant circuit. Now coming to example 10, a class C rectifier delivers PL equal to 600 milliwatt at to a load at V equal to 6 volt. The supply has a peak voltage Vm equal to 15 volt with a switching frequency of equal to 200 kilohertz. The allowed peak to peak ripple is in the DC output voltage is delta V equal to 330 millivolt. So determine the value of L, C and CF and the RMS and DC current for the inductor and capacitor. So given Vm equal to 15 volt, U equal to 6 volt, delta V 30 millivolt, F equal to 200 kilohertz and P equal to 600 millivolt. So considering the value of C equal to 15 nanofarad, so resonant frequency equal to F0 equal to this 200 kilohertz, and from which we get L equal to 42.2 millihenry, and load resistance we get RV square upon PL, so it comes putting value 60 ohm, and filter capacitor CF equal to I0 upon 2F into delta V, so getting I0 typically V0 upon R, that's 100 millihenry, and CF comes 8.33 microfarad. So PI RMS current of the inductor IL RMS equal to under root I0 square plus IM upon root 2 square. So IM is VM upon R, and that comes IM equal to 15 by 60 to 50 milliampere, and IL RMS equal to putting a value it comes 211.3 millihenry, and RMS current of capacitor IC RMS IM by root 2, that comes 176.8 milliampere. So these are the typical references which we followed preparing this this lecture, and thank you.